Does science generate truth? This may seem like a downright idiotic question, or something that philosophy is famous for, questioning the obvious and trying to contradict it. But this is meant in all seriousness. What does science generate? Oh, we take it for granted that we get scientific knowledge. But what is it actually that we're getting? Is it certain knowledge? Is it some kind of approximation of knowledge? Is it truth? Have we achieved, some kind of discoveries of the truths of the universe? How it is that the universe works, perhaps? All of these probably sound like familiar ideas, but they're very different ideas. And which one is actually an accurate representation of what it is that we're doing in science? Thomas Kuhn was one of the first to really develop this discipline or subdiscipline of philosophy, that is philosophy of science. And this came about around 1962 when he published The Structure of Scientific Revolutions. Now, Kuhn was a physicist, and so his perspective is one of an informed scientist, and I think this is important. So this is someone from within the field, not someone simply from philosophy looking over into another discipline and saying, hey, what are you guys doing over there? So Kuhn raises the question, what is it that we're really doing? Because he noticed that we generate what we think are truths, what we think is knowledge, and then later on we come along and revise it, or outright pitch it out and get something completely different. And this is the character of the history of science, is just this kind of thing, this revision and discarding of old discoveries of knowledge. But naturally, if you're revising knowledge, that means it was something less than absolute certainty, absolute knowledge to begin with. And if you're throwing it out, then it stands to reason that it wasn't knowledge at all. And the problem is, if you can't tell at any given time what it is that's going to be thrown out, then you really have very little concept of what it is that's knowledge. So this is a question that's asked in all seriousness and about the hardest of the sciences. In other words, we ask this question about physics and chemistry, and those things that we seem to, believe we have a good grasp on. We've seen in the past now how it is that those theories have been greatly revised and or completely tossed and corrected, as it were, or perhaps simply just supplanted with something different. And the problem is, if you can't tell the difference, and you can't tell for sure that you really progressed, then it's hard to say whether or not you have knowledge at all. It's hard to say that you have anything at all with respect to epistemological content, that is. So this is really a legitimate question from a philosophical perspective. Is science generating knowledge? Is science generating truth? Are we discovering it, in other words? Are we really discovering how the way that the world actually works? Kuhn also came to question whether or not science was a rational process. So he's cutting at some of the foundations of science here, and you can imagine how well this was received initially. Is science a rational process? And one would have to imagine that if anything in the world is a rational process, that it would be science. It at least tries to be, certainly. The problem is, the nature of scientific discoveries, as it turns out, creativity in the sciences, even the hardest of sciences, like I said, like physics and chemistry. And if we're thinking of things like mathematics, this is especially clear. How do people actually solve the problems? How do they solve the problems that no one has ever solved before? Not just recreating things that have already been done. But how do you solve something that no one has ever done? Well, you have to be creative, right? And if you have to be creative, then you are bringing about new material, and you're bringing about new material in any number of ways. Is there an actual method to creativity? And by the time we ask this question, it should become sufficiently obvious that no, probably not. And maybe science then proceeds to scientific discoveries using creativity, just as it's used in the arts. Is this really the case? When we discover something new, when we discover how to solve a theorem in mathematics, let's say, that has never been solved before, you can think of it as simply a recombination of theorems. And this is especially true in geometry, perhaps. But realistically, there's a lot of art, so to speak, and there's a lot of creativity that goes into trying to figure out how to solve something in mathematics that no one has ever solved before. And so one must be able to think in a way that is creative and not just enumerating possibilities. And the best mathematicians are not the ones that are best at enumerating possibilities. They are the best at creatively discovering, inventing new mathematics. And what Kuhn described was that this occurred in all of the sciences, and that all of the scientific discoveries at their root were actually very creative endeavors. The question is, can you differentiate that? Can you differentiate the process of scientific discovery from artistic creation of any kind? This is something of an open question, but I'll give you a hint at least. Is there aesthetics in mathematics? This is one of the questions that we're going to ask later in this lecture. Is there aesthetics in mathematics? In other words, is there such a thing as beauty in mathematics? And we think about mathematics as something, if there's anything farther from art, it would be hard to imagine it, right? But if there's still beauty in it, then maybe this leaves open the possibility for creativity in very much the same way. Obviously, you have rules and restrictions that govern mathematics, what you can and can't do, based upon what has previously been proven. But this is true for any system, for any discipline. So this is going to be true for chemistry, and this is going to be true for physics, but it's also going to be true for art. It's not as though you can just do anything. There are certain material restrictions that you have, technique that you have to study, and mathematics is like this. And creativity in mathematics then might be somewhat akin to, if not properly analogous to, the creativity in art. And this is one of the questions, this is one of the directions that this is headed. Now, back to Kuhn and the structure of scientific revolutions. You might notice by the title, we're talking about the revolutions in science, the upheavals, the changes, the dramatic changes from one way of thinking to another. And this is encapsulated in the idea of the paradigm. And you shift between one paradigm and another, so we have the paradigm shift. Now, you may have heard these terms. In fact, you probably have. There's something of buzzwords in business. And their use in business approximates the sense of what it is that Kuhn intended. Kuhn described paradigms as basically being little islands of perspective, such that they didn't share common ground with the other paradigms. And when you moved from one to the other, then, you couldn't compare the perspective from one to the next one. You might be able to compare some of the results. You might be able to compare some of the new calculations, the new methods of doing things. But ultimately, the perspective from one paradigm to the next, and that's what really informs whether or not you get knowledge, is fundamentally different, according to him. And so, one of the typical examples of this is in physics. When we move from classical physics to relativistic physics, and then to quantum physics, we're talking about very, very different ways of viewing the world. And not only very different ways of viewing the world, but maybe even very different ways of viewing physics. And this kind of fundamental difference, Kuhn claims, is such that the knowledge claims from one paradigm are not directly commensurate with the knowledge claims from the other. And what this results in is that it's very difficult to know whether or not you have knowledge. You simply have something that has a better or worse fit with the current paradigm, the current perspective on things. So physics has an overarching perspective of how they think the world works. And an idea is good insofar as it fits with that, and it works within the confines of that paradigm. And if it works outside of it, then, according to him, it's not going to be accepted. And it's not until you get enough data and enough of these things that come up where it looks like there are some holes in the current way of doing things that eventually the tension builds, and as he says, the peaceful interlude ends and the intellectually violent revolution begins. And what happens then is the old ideas are no longer in vogue, and then the new ideas come into fashion. And so then those that are going to succeed are going to be those of the new guard, the new ideas. So the classical physicists would have been very successful maybe in the 1850s, but by the time you get to the early 20th century, you may not be accepted quite so much. And conversely, with someone in forwarding something like Einstein's ideas, shall we say. So it takes a sort of critical mass, to borrow a concept in physics, before a discipline will experience one of these revolutions. And before it experiences that revolution, those that are thinking outside of the current paradigm are not going to be well accepted. And I think we can see this, that if you look at the way that especially the way the academic journals are structured, if you are writing too far outside of what it is that's generally accepted to be true in that discipline at that time, it's going to be very hard for you to get published. And because of that, it's going to be very hard for you to succeed, and so on. And there's sort of a cascade effect here. But it's going to be very hard for you to do anything in the discipline if you're thinking that much outside of it. And this is true for philosophy as well. Philosophy is certainly no exception to this, although it may purport to be. If your thinking is too much out of line with the way that people are currently thinking in the discipline, especially in a subdiscipline or an area or school, then you're not going to have very much luck succeeding, more than likely. Until such time as the winds change and a new paradigm is introduced, which happens periodically. And this was what interested Kuhn. What can we say from one paradigm to the next about a discipline? Is it actually progressing? Is it actually gaining knowledge? Now, you might argue that this is really obvious, and people cite technology as an example that obviously we are gaining knowledge. But that's gaining ability. We're able to do more things with the new approach. But that doesn't necessarily mean that it constitutes an advance in knowledge. So that's something of a question. And you have philosophers in the philosophy of science that vary greatly on these topics, all the way from Feyerabend, let's say, who denies scientific knowledge essentially entirely. And Kuhn is something on the other side. He doesn't seem to be quite so resistant to that, even though he basically started the discipline. Now, I have some examples for you there. We talked about Newton and Einstein with classical and relativistic physics, but we can take a look at some others. The phlogiston one with Lavoisier and oxygen is very interesting because these are two competing theories essentially for the same kind of phenomenon, but the perspective required for each one of them to work is very different. And if one of them works, the other one doesn't. So it's easy to see how it is that if you're working within the paradigm, then you're okay as long as that paradigm is entrenched. But as soon as it switches to the other one, it's a completely different climate. And this is the kind of thing that Kuhn was talking about. Now, this invites a certain amount of question with respect to just how different are the paradigms and what constitutes a paradigm shift. I mean, simply, a view on oxygen in chemistry, is that enough to constitute a paradigm shift? Or does it have to be something more comprehensive, like relativity? It's hard to say. Would it be completely a completely different discipline if it changed that much? Ptolemaic and Copernican astronomy that's a pretty big difference between those two perspectives, especially world perspectives there, because we're talking about essentially the Earth being the center of the universe, and then no longer. So this is really an open question in philosophy of science. How much difference is there actually from science from one era to the other, in science from one era to the other? So to recap, Kuhn describes the cycle as proceeding from the normal or puzzle-solving state to tension building up and then a sudden revolution. And then there's a new normal established according to the new paradigm. And then you have another puzzle-solving state where people are basically just working out the details of the new paradigm until it doesn't quite work, and tension builds up, and then you have another revolution, and then on and on again. And in the state immediately prior to the revolution, you have discoveries, or you have experiments that are done that where the results don't make much sense. And the discoveries that are made are somewhat counter to the assumptions and incompatible with the previous perspective. And these anomalies are essentially explained away. They're ignored, not published, or somehow dealt with until such time as the discipline reaches critical mass, and you have a revolution, and a new paradigm is put in place to deal with all the anomalous behavior. So, given that this is happening, and we can see something like this happening, now whether it's to the extent that he describes as far as the incommensurability thesis or not, is something of a question in philosophy of science. However, that there are periods of relative peace and then revolutions, I think, is intuitively obvious to anyone who looks at the history of science. The question is, in this evolution, in this process, is there any progress? Are they evolving towards something? Now, again, technology is an obvious counterexample that people like to give, but this isn't something Kuhn was unfamiliar with naturally. As was stated earlier with the ability and progress remark, that when we're talking about technology, we're just talking about new abilities that have been gained. We're talking about new things that we can do with it. We're not necessarily talking about new truths or new knowledge. So he suggests that progress, as we typically think of it, is not really what's going on in science. And in fact, if we look closely enough, that what you're going to see is basically just work within the current paradigm and refining of the current paradigm. And there are still anomalies that we can't deal with properly, and there are still things that are left unexplained. And until such time as we reach enough of these so as to cause a problem for the discipline, and someone has a better explanation, then we'll continue in the current paradigm. One of my favorite ways of describing some of how the technology and approximation argument works in physics, and this is something that is perhaps intuitively obvious if you look at it for very long, but may not be manifest to your average person if you don't have very much experience with physics and chemistry and the sciences in general and how it is that they solve problems. For physics, for instance, if we have a problem that says, okay, describe the gravitational influence of the moon on a cow that is orbiting the moon. So you've got this cow orbiting the moon. How do you describe this in terms of the physics that we know? How do you set it up in equations? And very likely the first thing that the physicist is going to do is say, okay, no problem. Assume a spherical cow. Or rather, assume a point mass. So either assume the distribution is perfectly homogeneous, or assume a point mass so that we don't have to worry about the arm or the legs and ears and nose and whatnot of the cow. Because even though the gravitational effect is slightly different, since the range is slightly different, it's really of very little consequence, because the mass of the cow is so small compared to the moon that it's not enough of a difference to worry about. And that's the kind of thing that we continually run into with physics. In fact, simplification of certain equations can be done in this way. If we are satisfied that under a lot of conditions, for instance, under normal, like if we were trying to describe elements of a car crash, for instance, it may not be necessary to use the relativistic versions of some of these equations. So we can assume that the speeds are much less than the speed of light. So we don't have to take into account some of the additional complexities, and we can avoid a lot of additional problem for ourselves in doing so. And this kind of approximation is really the norm in the way that physicists and anyone who uses physics and engineers solve these sorts of problems. So that the technology that we get from these things is really a result of a series of acceptable approximations frequently. Now, I suppose you can work with it to the fullest extent of whatever it is that we happen to know, but the refinements tend to be made on the margin there, and frequently for special cases, such as when the speed of the object is near the speed of light, or is a significant fraction of the speed of light, shall we say. Such then that relativistic effects would have to be taken into account. But most of the time, for a lot of situations that we're very accustomed to, we use versions of equations that essentially have these assumptions built in. And this doesn't really bother us because it doesn't affect our calculations except maybe down to the fifth or sixth decimal place. So it really doesn't matter for most of what it is that we're going to do. And so the technology that we have frequently, when we're designing some of these devices, let's say like a light bulb or something of the kind, there are a lot of details in the equations that we don't necessarily have to deal with because we can make some of these sorts of assumptions. If a number is very, very, small in comparison to another number, or, this sort of thing. And what this basically tells us is that we're going to get the technology even if we don't have the truth, because we're explicitly ignoring certain parts of it because it makes the mathematics messy. And it's really not important enough to where it's going to matter. So when I'm manufacturing the thing, let's say, the tolerances of my tools may be larger than the error generated by not taking into account, the relativistic speeds or something that's, really and truly almost completely irrelevant to whatever problem I'm trying to solve. But nevertheless, if I was to, get to brass tacks, so to speak, then I would want to know what the actual equations were that governed, the motion or the whatever it is in the problem that I'm trying to solve. But you see, for creating things, it's not always necessary. And because of that, it's possible for us to have technology and us to make advances in technology without actually having any truth about what's going on. In other words, we may have nothing but approximations, and we may know that we have nothing but approximations, but we can still do some really cool things with it. And that's the nature of technology, so that the technology that we create then is truth independent, so to speak. And this allows someone in philosophy of science to say that, the technology that we get from this is wonderful, but it, in and of itself, it does not provide a counterexample to the claim that science is not generating truth. All right, let's move on to the philosophy of mathematics for a bit. Philosophy of mathematics is kind of a fun thing. This is an unusual bit of mathematics. We're used to dealing with the, how do I solve this equation, and how do I deal with this expression, and what can I do with this series, and whatnot, and the details of mathematics. But the philosophy of mathematics, at least in part, deals with some of the overarching questions that mathematicians, to be perfectly honest, just don't really bother with most of the time. But they are interesting and relevant things to think about when it comes to, what is mathematics? What are we actually doing? Because ultimately that doesn't really matter for the mathematician. He's still working within the confines of his system. What I mean by this is, for instance, questions like, where does mathematics come from? Now that seems to have a very obvious answer. It comes from nature, right? I mean, 1, 2, 3, 4, 5. I can count my fingers. I can count apples. I can count whatever. But seriously, the objects that we recognize are dependent upon our system of classification. They depend upon the objects actually being separate. And so for something to be countable, it needs to be separate from something else. If you just have an undifferentiated mass of energy, then it's not going to be very interesting to count things. So the question is, does our notion of number and our general principles in mathematics, are these things simply reflections of the way that we think? Or are they in fact reflections of the way that the world actually is? So does the world run on numbers? Or is it just something that's very convenient for us and works for the way that we think because our minds are used to classifying things for us and picking out objects? Object recognition is one of the supreme talents that our brain has, so to speak. We very quickly assess a situation and pick out individual objects and distances and sizes and, motion and this sort of thing. And this is crucial for obvious reasons, I should think, for survival, for creatures in general. But that doesn't tell us anything about the way that the universe works. That tells us about how our mind works. So just because our mind is comfortable with separating objects doesn't mean that the nature of things is such that those things are actually separate. In fact, the physics, as present in quantum physics at least, with the ideas of interdependence and not being able to look at things in isolation, not being able to truly look at anything objectively, apparently, it makes these notions very difficult and very vague, you might say. So it's a relevant question for us, I think, again. Why is it that our notion of number, first of all, where does it come from? Where does a notion of number come from? And secondly, why does it work so well? I mean, obviously, if I'm counting apples or if I'm counting my fingers, I mean, there are certain things that don't require much brain power to, identify the utility. But why is it that the equations that we have found to describe various things, mathematical relations, let's say, including those in geometry, and then, of course, the applications of calculus, such as physics, why does this work so well? We're able to do some pretty spectacular things because we think that we've got the numbers down to the nth decimal place when it comes to our calculations on how to do something. For instance, flying around the moon. I'm sure you've heard the famous exchange between the astronauts in Houston, who's flying? And the response was Newton. Because ultimately we understood the laws of motion so well, or at least closely enough, that we were able to accomplish something really pretty amazing. Now, why does it work? It's interesting that it works, but why does it work? Why are we even able to study physics? Why are we able to apply mathematics to it? It's not intuitively obvious that the world should be mathematical. Now, if you look at certain aspects of the world, that leaves tend to have the same number, same number of points, unless, of course, we're talking about 3- and 4-leaf clovers, right? But in general, nature exhibits a lot of symmetry. It exhibits a lot of apparently clever uses of number. And why is it that it matches so well with some of the concepts that we have, especially if they're very simple concepts? And one of the examples that I like for this is the golden ratio. And you can see a few examples of this on your PowerPoint slide. You can see how this is calculated. And there are a number of really unusual ways. The three that are listed over to the right are particularly strange for calculating this. Why should those result in the same number? And why is it that number should appear everywhere in nature? That's something of an unsolved mystery, because this is a really kind of an unusual number. It's an unusual proportion, and we see it everywhere. The shells, the nautiloid. We see it in a lot of different plant and animal symmetries. And as it turns out, which you'll learn if you take art history, this sort of proportion is also used in the creation of classical art. So positioning of figures and, parts of a scene and, the horizon line and whatnot. As it turns out, the golden ratio creates a very pleasing arrangement for us. And this can be done in any number of ways. You can use it, several times and subdivide again. And that tends to work out fairly well. And just the fact that it tends to work out in an aesthetic way, in addition to the fact that we see it all over the place in nature, is just really weird. Why is it that this happens? Does this give us some confidence that the mathematics that we are doing and that we have discovered, let's say, or created, depending on your perspective, does that mean that mathematics actually relates to nature? It actually reflects nature. It is a discovery of sorts about the way that nature really works. The concept of zero is a fun thing, and this is one thing that I wanted to mention because it's so unusual, and this is something that people, I think, don't entirely guess very easily when they're thinking about these problems. or when they're thinking about mathematical history. We didn't have a zero for a very long time. And only certain cultures, for whatever reason, developed this mathematical technology. For instance, do you know what the Roman numeral is for zero? Now, if you're particularly clever, you may have said N for nulla, for nothing. This is something of a late addition. There is no real Roman numeral for zero, not originally at least. If you think about it, the Roman numerals don't need a zero. They don't need placeholder values. Where we have 10 and 50 and 100 and 1,000, they don't need those placeholder zeros. So it doesn't have the same meaning. That is one of the things that makes doing multiplication and addition and subtraction and division and basically any mathematical operation somewhat difficult using Roman numerals. And there are a lot of special techniques that you can learn to deal with that. But ultimately, it's something of an awkward system for doing mathematics. And you might say that where we saw mathematical progress in the history of mathematics with different cultures is where we tended to see a setup. In other words, a base n system where n was something that was actually convenient. Base 60, as it turns out, works fairly well. 60 has a lot of factors. It's divisible by 30, 20, 15, 10, 5, 2, 3, 1, and so on. And that makes it convenient for doing a lot of calculations. And so this allows for perhaps a bit more, a bit of ease in doing mathematics compared to a system like the Roman system, which is actually somewhat clunky for doing any kind of real mathematical work in. So it is kind of interesting that we don't really see a zero. In fact, in the West, we don't see a zero for a very long time. We don't see this as a fully developed concept until about 1200 or 1300 AD, which is an unusually long time, I should think, considering how highly we regard the West with respect to our accomplishments, especially in the sciences. Now, if we contrast this with the dates that we have, for instance, for the Olmec phenomenon, they had a true zero at about 400 BC. So this is a good 1600 years before we had it in the West, which is awfully curious. The Babylonians actually had they were the first to come close, at least. They used a space at first to denote a placeholder for zero, essentially, where there should have been a zero. They used nothing, essentially, which is natural for a concept that refers to nothing. But this is confusing, so you need to have some kind of character placeholder for this, and we see this around 1500 BC. The Greeks did a little bit better. Ptolemy, apparently around 130 AD, did use a character for zero that stood alone. In other words, that could mean nothing. That wasn't just a placeholder. So this is a true zero, so to speak. Now, this was the second that we know of. The Olmecs also had a true zero, as I mentioned. The Romans, to give a bit more precision to the story, were behind. And the first time we see this is about 525 AD. But that's still using the word nulla instead of a character. And we don't see the use of the character in until about 725 AD, when it was used to try to compute the dates for Easter. So very much behind. And like I said, this didn't trickle to the remainder of Europe for hundreds of years after that. So it's curious to see just how this progressed in societies that existed for a very long time without this mathematical technology. Well, why do you need it, though? I mean, if you think back to, put yourself in Roman shoes, why do you need a character that stands for nothing? I mean, what good does that do you? It refers to nothing, right? So in the mathematics, obviously, I mean, Roman numerals were adequate. They certainly did not make it easy, but if you didn't know anything else, even there, it would seem like, nonsense to suggest that you needed a character that stood for nothing. Why would you talk about nothing? So this is an aspect of mathematics that's it's not entirely intuitive at first. And I think just seeing how, not necessarily counterintuitive, but at the very least unintuitive it is kind of impressive. And when we see when we see societies that have achieved this sort of thing and have started to work with it, we see advances in mathematics. The Babylonians were unusually good mathematicians. And so it's for things like this that when we look back in mathematics, a lot of it seems obvious to us because we're so familiar with it today. You know, how could anybody have not had that sort of notion, the notion of a zero? And if you're a mathematician today, you may look back and say, well, how could you not see some of the notions, for instance, with maybe infinite sequences and series? A lot of it does seem fairly intuitive. It's not very hard to understand. But if you don't have it at all, in many cases, even with the zero, it's not as simple as you might think.